Beginning Algebra, Section 1.2. The first section is on inequality and equality symbols. The inequality symbols are greater than, less than, greater than or equal to, less than or equal to, and then your last inequality symbol is the not equal to. So all 5 of these are what we call the inequality signs. And then you have the equal sign. Okay, you need to be able to use these signs, know what they mean, be able to read them from a problem. Like number 1, if you have 11 is less than or equal to 11. Okay, notice that it's open to what would be normally the larger number. So again, you read this, 11 is less than or equal to 11. Is that true or false? If either one of those conditions would be true, then we could say the whole statement is true. So because 11 equals 11, this would be true. Number 2, 8 is less than or equal to 9. Okay, excuse me, 8 is greater than or equal to 9. This would be a false statement because 8 is not greater than 9, 8 is not equal 9. Number 3 says negative 11 is greater than negative 10. Whenever you're talking about negative numbers, it may help if you refer to a number line. On a number line, we typically say 0 is in the middle. All of the numbers to the right of 0 are positive, and those numbers are going to increase as they go to the right. All of the numbers to the left of 0 are negative. The further you go to the left, the smaller the value of that number becomes. So if we go back and look at negative 11 is greater than negative 10, negative 11 would actually be less than, so this statement would be false. Part 2 says to translate sentences into mathematical statements. You need to be able to use the symbols given here to write an algebraic statement with those sentences. So number 1 says 7 is less than 11. So we would write 7 is less than 11. Number 2, 5 is greater than or equal to 4. 5 is greater than or equal to 4. Number 3, 20 is greater than 2. 20 is greater than 2. Number 4, negative 7 is not equal to 7. Negative 7 is not equal to 7. Okay, this is called translating a sentence into a mathematical statement. So you have to make sure that the mathematical statement you write is equal to or means the same thing as the sentence that's given to you. Part 3 deals with identifying the sets of numbers that are used in mathematics. There are 6 sets of numbers. The first one is what we call the natural numbers. To me, the natural numbers are the numbers that you count with. So I often call these the counting numbers. If you're going to count something, what would you start with? Positive 1, 2, 3, 4, and so on. We could continue counting forever. We use the set notation. This means that the natural numbers are the set of numbers beginning at 1, going forever in the positive direction. The whole numbers, by definition, are going to be the set of numbers that begin with 0 and then continue in the positive direction. So could I say that 4, we know it's a natural number, is it also a whole number? Yes. Okay, you can classify numbers into different sets. They're not just strictly in one group. So all of my natural numbers are also whole numbers. Integers is our third set, and to me when I think about integers, I think about the number line. Again, 0 in the middle, everything to the right positive, everything to the left negative. Those numbers that I see along the number line are actually what I would call the set of integers. They include both positive and negative, both positive and negative whole numbers. So integers are can be negative, include 0, and are positive. If I was going to write the set notation, I would have the dots in both directions. This means forever negative, including 0, forever positive. But no fractions are here in the set of integers. They're just what we would call whole numbers, no fractions. The rational numbers are actually going to include these three sets above plus the fractions. But it's only certain fractions. We said that rational numbers include fractions that terminate or repeat. Fractions that terminate or repeat. For example, if I have 12 over 3, that's a fraction. If I divide this, 12 divided by 3 would actually equal 4. That's a terminating fraction. It's just 4. It stops there. That's a rational number. If I have 1 divided by 3, if I were to divide this out, it would be 0.333, and it would continue. It would repeat. These would both be what we would call rational numbers. If I have, let's say, the number 5, it's also rational because it can be represented as a fraction. 5 is understood to be over 1, so that makes it rational. Okay, therefore we can say, let's look up here, if I take number 4, it's a natural number, it's a whole number, it's an integer, and it is a rational number. Okay, is every rational number going to be an integer? No, it doesn't work that way. If I look at 1/3, 1/3 is rational, but it's not an integer. But if it is in one of those three sets above, it would also be rational. We have another set of numbers called the irrational numbers. We don't use these a whole lot in this course, but you do see them in later courses. These are fractions that do not terminate or repeat. Fractions that do not terminate or repeat. For example, the square root of 2. If you were to type that into a calculator, it would give you a long decimal number that would have no pattern to it. Or pi. Typically we say pi is equal to 3.14, but it's actually a very long decimal that does not terminate, does not repeat. A number cannot be both rational and irrational. It has to be one or the other. And this last set is the set of real numbers, and this is pretty much what I call the easy one. This is all of the sets that we've talked about. Every number that we're going to talk about in this course is going to be a real number. So if I give you a number such as 7, you're going to need to be able to classify and tell me which sets it would fit into. Okay, so 7, if I look at my diagram, this kind of shows a relationship between the numbers. If I start with natural, is 7 a natural number? Yes, it's a counting number, which also makes it a whole number. Is 7 an integer? Yes, and therefore it is rational. So if it belongs in the natural number, it's also going to be these other three. If it belongs in a whole number category, it's also going to be an integer and a rational. If it's an integer, then it's also going to be rational. And then a number that's rational would not be irrational. That's why we kind of have that setting out to the side. And then all of these together are considered to be the set of real numbers.